In the past, there have been quite a few measurements of the polar ice caps using radar techniques and other techniques, but they generally are not acquired synoptically, that is, all at once over the period of a month. So, for example, you might have one satellite or ground campaign measuring one set of glaciers over one part of Antarctica, and then some years later they might measure another piece. And the scientists in the past have put all of these together into a, shall we say, a comprehensive velocity field that's cobbled together over many years. So you're not looking at the dynamic changes in the flow of the ice. What you're looking at is sort of an average flow of the ice over a period of years. But we all know from looking at imagery of the ice sheets that there are dynamic changes occurring spatially and over time. So if you really want to understand the physics of how the ice is changing, the snow coming from above and the ice flowing out into the oceans, and how that's changing over time, so you can understand the actual dynamics, how the bed of the bedrock below the ice is affecting that flow, how the heating of the water around the perimeter of the ice is affecting that flow. You need to make more time series measurements comprehensively so you get the big picture. And that's what NISAR can provide. It will be able to improve these models by getting a synoptic view every month or so over the life of the mission. So, synthetic aperture radar. Most people think of radar as the instrument that a policeman has in his car looking at your car speeding down the freeway. So he sends out a pulse of energy towards your car. It bounces off your car and it comes back to the policeman, and he receives that energy. And from that he can tell how fast you're going, he can tell how far away you are if it's a good enough radar. And it's basically just a little pulse of energy. So we do the same kind of thing to make an image with radar, but we have to do some extra work in order to create the image. So we're flying our satellite along its orbit, and it's sending out a pulse of energy, just like the radar speed gun. It bounces off the Earth, and some of the energy comes back to the satellite. We move along the orbit, and we measure another pulse. And we do this literally 1,000 to 2,000 times every second. So aperture generally means an opening, and it's another way of saying antenna. It's a fancy way of saying antenna. But with that antenna that's on the satellite, we can only achieve a resolution, an imaging resolution, which is on the order of many kilometers. So we want better than that. So what do? We have to create an antenna somehow in space that's much, much larger, because the larger the antenna, the better the resolution that we can create on the ground. So we take this physical antenna, which is maybe 5-10 meters in space, and we create a many kilometer antenna from it by this synthetic aperture technique. And the technique is to effectively fly the spacecraft along its track, send out pulses 1,000 to 2,000 times every second, and take all of that information that comes back to us over many thousands of pulses and treat it with special mathematical techniques as though they were all acquired at the same time by one big antenna. So we synthesize a very large antenna from many small antenna observations over time.